This PowerPoint talks about velocity. There are two types of velocities that we're going to be talking about. One is instantaneous and the other is constant velocity or average velocity. Instantaneous velocity is a velocity at any given time. Usually we use graphs in order to determine the velocity at that point in time, or we can use calculus. Now, velocity may be changing. You may be getting faster or slower, but the instantaneous velocity is just that velocity at that moment. Average velocity is the total displacement divided by time. Now, if we have, we're going a certain distance and we may be speeding up or slowing down, we take that total displacement, divide it by the total time over that displacement, and that's going to give us our average velocity. There's really no other way to figure out average velocity. In math class, when you hear the word average, you may think of taking several numbers, adding them together, and dividing by the total number of numbers that you have. But in velocity, in physics, we cannot do that with velocity. We have to take the total displacement and divide it by the total time. Now the equation for average velocity, which this little bar over the v, that just means average. The average velocity is going to be equal to displacement divided by time. And if you remember the delta x, the delta means change in and the x means position. So this is change in position, which is the definition of displacement. Displacement divided by time is going to be equal to our average velocity. Now, for the purpose of just being consistent with each other, that we're going to go by what's called a convention, and that is that as scientists we're going to choose something or a way of measuring something in order to standardize it between two scientists. For example, velocity includes a direction. Now for this class, we're going to say that to the right is the positive direction and to the left is the negative direction. Now there's nothing in nature that says the left has to be negative. As a matter of fact, if you're sitting at your table right now, you can look across at somebody that's looking at you, and your left and their left are in two opposite directions. So left is going to be considered negative for the problems that we're going to be doing. When we do labs in class, you may have to be a little bit more specific about directions, like to the front of the classroom is positive, to the back of the classroom is negative. But this convention we're going to be using throughout the course, that the left is negative and right is positive. Now if we take this equation, the average velocity is going to be equal to displacement divided by time. Remember, change in position is final position minus the initial position. Multiply both sides by time, and you get that velocity times time is going to be equal to final position minus initial position. Add the initial position to both sides, and you're going to find that the final position is going to be equal to average velocity average velocity times time plus the initial position. Now this is just another way of writing the equation that looks probably a little bit more familiar. If you're in a math class, you may have seen this format right here. This looks a lot like a y equals mx plus b format. So you can actually look at this and see that m, the slope of the graph of a position versus time graph, is going to be equal to velocity. The y-intercept is the initial position, which should make sense because that's the position when time equals 0, when you're at the y-axis. So this is essentially a y equals the slope times x plus a b, a y-intercept. Now what is a car's velocity? This is kind of a trick question because we just said that there are two types of velocities. We're talking about instantaneous velocity and average velocity. Well, let's take this example. We have a car that's driving from this end to the midpoint here going 100 miles an hour for 50 miles. This person stops for an hour for one reason or another, then gets back in their car and they drive for another 50 miles at 100 miles an hour. Now if we look at the time here, 100 miles an hour for 50 miles, that's going to be half an hour. And then they stop for an hour here and drive another 50 miles at 100 miles an hour, which is going to be another half hour. That's a half hour plus an hour plus another half hour. That's a total of 2 hours. Now if we look at their instantaneous velocity during this part is going to be 100 miles an hour. During this part is going to be 100 miles an hour. But at this point right here it's going to be 0 miles an hour. However, if we look at the average velocity over the total displacement divided by the total time, the total displacement is 50 plus 50 miles, which is 100, divided by the total of 2 hours. And we get that the average velocity is going to be equal to 100 divided by 2, which is 50 miles an hour. So that kind of shows the difference between an instantaneous velocity and an average velocity. Example problem number 1. Let's suppose a man is on a bike and he travels a constant velocity of 4 meters per second north for 5.0 seconds. What is the person's displacement? If you look at this, if you remember, displacement divided by time equals average velocity. Well, right here it says that his velocity is 4.0 meters per second. And using the word constant velocity is pretty much the same as average velocity. Sometimes we could have a changing velocity, but the average velocity would be equal to the constant velocity, which is displacement divided by time. So if we take the displacement divided by time, multiply both sides by time, bring time to the other side, we get velocity times time equals displacement. Well, in the equation we got velocity, we got time. Let's go ahead and plug them in. 4 times 5 gives us 20 meters, and because it is north, then that has to be included. Displacement is a vector. We're going to get to vectors later on, but essentially speaking, this is a measurement that has to include a magnitude or an amount along with a direction with it. Example problem number 2. A ball is rolled at a constant speed away from the wall. When it is 3.8 meters from the wall, the time starts. At time equal to 5.64 seconds, the ball is 14.2 meters from the wall. What is the velocity of the ball? Now, there's some information that's given here. It says at 3.8 meters from the wall, the time starts. Based on that, you should indicate that the 3.8 meters is the initial position. And then when time is 5.64 meters, the ball is 14.2 meters from the wall, which you should indicate is the final position. So if we go to the equation, final position equals velocity times time plus the initial position, and then we plug in what we know. The final position, 14.2, the time is 5.64, and the initial position is 3.8. We need to rearrange this so we figure out the velocity. We're going to subtract 3.8 from both sides, and then we're going to divide by 5.64 from both sides, and that gives us a velocity of 1.84 meters per second away. And because velocity is a vector, it does need to include the direction, and we are moving away from the wall. That's going to be our direction. Example problem number 3, a car moving at 50.3 meters per second starts being timed at 40.2 seconds away from point A. Now, we have the velocity right here. That's going to be our average velocity or constant velocity. 40.2 meters from point A is when the time starts, so that's going to be our initial position. How far from point A will the car be at 5.9 seconds? That's going to be our time, assuming linear or straight line motion. Now there are going to be examples where we have motion back and forth or in a circle, and that gets a little bit more complicated, but we're not going to deal with that right now. We're just assuming it's going to be in a straight line. So we start with our initial equation. Final position is going to be equal to velocity times time plus the initial position. Then we're going to plug in our numbers. We know the final position is going to be equal to the velocity, which is 50.3 meters per second, and times the time, which is 5.9 seconds, and then we add on the initial position of 40.2 meters, and then we add that up, we get 337 meters, and we do need to include the direction, which is away from the wall. At a Stockholm motorcycle fair, a graphic demonstration of a collision between a Honda motorcycle and a Volkswagen was placed by a Swedish police and road safety department. It was determined that the cyclist was driving 155 miles an hour when he collided into the Volkswagen. With a normal reaction time to see, decide, and then react of about 1.6 seconds, how far did the cyclist travel before he could react? Well, if you notice, we're dealing with miles per hour and we're dealing with 1.6 seconds. So before we get these two in an equation together where we have velocity times time, we got to get the units right. Velocity, 155 miles an hour. We're going to take the miles and we're going to convert to feet. So 5,280 feet equals 1 mile. The hours into seconds, 3,600 seconds in 1 hour. That gives us a total of 227 feet per second. All right, so our units are now right. We take 227 feet per second, multiply by 1.6 seconds, as a total of 363 feet. Now, if we want to convert that to meters, then we take 363 feet. 1 foot equals 12 inches, 1 inch equals 2.54 centimeters, 100 centimeters equals 1 meter, so that's 111 meters. Now to give a little reference on this, 363 feet is about the length of a football field, including the end zones. So this cyclist, before he could even begin to stop, He traveled the length of a football field, including the end zones, and that's before he even applied the brakes. This is the picture of the collision that took place between the motorcycle and the Volkswagen. Can't really see the motorcycle, but that's because the motorcycle is inside the car. Another perspective of the motorcycle inside the car. And that's a pretty good perspective of how it crashed straight into the side of the car. The sign above the display also noted that the rider had only recently obtained his license. At 155 miles per hour, police predicted that the rider's reaction time once the vehicle came into view wasn't sufficient enough for him to even apply the brakes. The car had 2 passengers and the bike rider was found inside the car with them. All 3 involved, the 2 in the car and the rider, were killed instantly. The Volkswagen actually flipped over from the force of impact and landed 10 feet from where the collision took place.